last section of Chapter 4, we're looking at a topic that is very closely tied to science classes. And you'll see this in many of the examples, and that's variation. And there's two kinds of variation. Direct variation is when one thing gets bigger, the other one gets bigger. One thing gets smaller, the other one gets smaller. They are directly related. Now here's some examples of things in nature, in science, that are just directly related. An object's weight on the moon varies directly as its weight on Earth. We use this statement to convey the idea that if something's small on the moon, it's going to be small on the Earth. If it's big on the moon, it's going to be big on the Earth. They are directly related. Same thing with a spring. If you have a spring, if you pull on it a little bit, it stretches a little bit. If you pull on it a lot, it stretches a lot. And so that's what they're talking about. Now specifically, we want to see how we can transform these sentences into mathematics. And so look, we're going to use the object's weight on the moon as the letter M, and here's the whole idea. The term varies means we create an equation that says equals k. The k represents a constant. You'll see in just a moment the name of that. And the weight on the earth is the letter E. So we have M equals k times E. That is that sentence. The next one says the distance a spring stretches, we'll call that D, varies equals K, and the force F. D equals K times F. The last one says the pressure P varies and directly as the depth. P equals K times D. Here's the word I was telling you. These are referred to as the constants of variation or the constants of proportionality. For the moon, that is a known quantity. The relationship of the weight of an object on the moon and the weight of the object on the earth. Many of these are things that can be looked up in tables, or we can experiment to find them, as I'll show you here. If an object's weight on the moon varies directly as its weight on Earth, then we have this equation, which, by the way, it'd be the same equation if we was talking about Jupiter or Saturn or any other planet. However, if we are told here is an observation, an astronaut and their equipment weighed 360 pounds on the Earth. When they got to the moon, it showed 60 pounds. That is not like a super diet or anything. That's just the relationship between the two. And so, if we take the equation, we will use the numbers 360 for the E and 60 for the M and compute the constant. And again, this could be looked up in a table if you had such a thing. And so we know everything weighs 1/6 on the moon what it weighs on the earth. However, we just plug that into our equation in place of the k. And we have a new equation. M equals 1/6 E. This is valid anytime we're talking about moon and earth weights. And so now we're prepared to answer any question that comes our way, like this. And so we take our new equation, use the 186 for E, and do the calculation. So a person who weighs 186 pounds on Earth is going to be 31 pounds on the moon. Now here are some to just experiment with and show you some variations that you might see. For example, this would translate into y equals k and x squared. This one would say s equals k and t cubed. This one would say f equals K and square root of D. See how easy it is to write the equations from the statements of variation. Now, inverse variation is when we have two things that are related in such a way that one gets bigger, the other one gets smaller. For example, the water temperature in the ocean is inversely proportional to the depth. That means the small depths give big temperatures, and the big depths give small temperatures. They're backwards of each other. And here's the same thing that we just did. The temperature is T, varies is equal K, and here's where it gets different. If it says inverse, then we create a fraction with 1 over that. And so our equation would say T equals K times 1 over D, or T equals K over D. And here's the same thing that we just did, and we'll go through it a little bit quicker. If we're given an observation, we plug those numbers in and compute the K. We then rewrite our equation and we answer questions. Here we just take our new equation and plug a 5,000 for the D and type that into our calculator. Here's somewhat to experiment with. F varies inversely 1 over D squared. How about Y varies 1 over cube root X. Now here's a problem directly from the homework. I've highlighted a few key phrases. We start by translating the intensity of light. We'll say I varies inversely. That's 1 over D squared. We take the next numbers and plug them in. For I, we'll use 97. For D, we'll use 18. And we solve for K. Multiplying both sides by 18 squared, here's what we get for K. We rewrite the beginning equation with that in place of K. And we answer the question. At 9 feet, that means D is 9, we would have I is 388. Now that's the general guide. Now the last one is when we might have several, 2 or more, combined in the same thing. For example, if Y varies directly as X and inversely as Z, we start with the Y, varies is equals K, directly as X means just times X, but inversely as Z means 1 over Z. Now we could write that as Y equals KX over Z. Here's another one. We got V varies directly times H, and notice there's no inverse in this one, R squared. Only put 1 over if it says inverse. And so let's go through one off of the homework again. Starting with the top, the volume V varies equals K. Directly means T. Inversely 1 over P. Second sentence, in place of the V, we're going to use 30. In place of the T, we're going to use 300. In place of the P, we're going to use 20. And solve for K. Rewrite our original equation. And then answer the question. T is 320. P is 32. We would get 20.